Okay, so we've looked at a couple of fairly standard induction examples now. Let's actually look at a couple of ways that we can generalize induction a little bit further than than what we've done so far. And these aren't really very complicated generalizations, and indeed one can show that they're actually equivalent to the original induction statement. But these are formatted in a way that makes them quite useful in certain cases. So let's look at two simple generalizations of the induction method that we've seen previously. Okay. So here's a simple generalization of mathematical induction. So first thing we're going to do is let L be some fixed integer from Z. Okay, so no longer a natural number. L can be any integer. And let's set S to be the set of all integers bigger than or equal to L. Okay, so what we're going to do here is we're going to move induction from starting at 1 to starting at some fixed integer L. And that's the only difference. So let P of n be a statement for all n in S. So now instead of being a statement for n bigger than or equal to 1, we're going to let it be a statement for n bigger than or equal to L. Well then, if P of L is true, so instead of starting at 1, we start at L, and P of k implies P of k plus 1 is true for all integers k in S. So now again, instead of just from n bigger than or equal to, or k bigger than or equal to 1, it's now bigger than or equal to L. Then P of n is true for all n in S. And so all we're doing here is making induction start from L, where L is some fixed integer, rather than starting at 1. So what we've done really, if you think about it, is just moved things across, okay, to start at L instead of starting at 1. And so really the main difference here is that our base case has to change. So let's look at some simple result here. So another useful little result: for every integer bigger than or equal to 5, 2 to the n is bigger than or equal to n squared. And if you think about this for a moment, this makes sense that n squared is growing quadratically, it's growing like a polynomial, whereas 2 to the n here is growing exponentially quickly. So you'd expect this to be true when n is big enough, and here big enough it turns out to be 5. So let's look at a proof. So we prove the result by induction. Well, we first have to check the base case. So we check now when n equals 5, 2 to the 5, which is 32, is definitely bigger than 25, which is 5 squared. So the result holds when n equals 5. So that's our base case. Okay? So now we're going to play around with what happens when it's true for P of k. So namely 2 to the k is bigger than or equal to k squared when k is bigger than or equal to 5. So we're doing our same inductive step, just now instead of k being bigger than or equal to 1, k is bigger than or equal to the place that we start, which in this case is 5. Well, let's look. We need to say something about 2 to the k plus 1. So we can take this inequality here and just multiply it by 2. So if we multiply it by 2, we get 2 to the k plus 1 is bigger than or equal to 2k squared. Now what do we want to show? We want to show 2 to the k plus 1 is bigger than k squared plus 2k plus 1, because that's k plus 1 squared. Well, let's start massaging this right-hand side to make it look like the thing that we want. Well, we can write this as k squared plus k squared. So we'll reserve this k squared and then start playing with this. Okay, so we've already made the right-hand side look like the right-hand side that we want. Well, k squared is definitely bigger than or equal to 5k because k is bigger than 5. So 2k squared is bigger than k squared plus 5k. So all I've done is massage things around to try to make the expression that we have look like the expression that we want. And so I'm just sort of cutting away bits and pieces until we get down to what we want. Well, 5k is equal to 2k plus 3k. So now I've made the right-hand side look more like what we have here, k squared plus 2k. And now we just have to worry about this 3k. Well, 3k is definitely bigger than or equal to 1 because k is bigger than 5. Indeed, this is bigger than 15. So this expression is definitely bigger than or equal to k squared plus 2k plus 1. So we've shown that based on our assumption that k is bigger than 5 and 2 to the k is bigger than or equal to k squared, that 2 to the k plus 1 is bigger than k plus 1 squared. So the inductive step holds for k is bigger than or equal to 5. So we've shown the base case when n equals 5 is true, that P of k implies P of k plus 1, and so the result holds by induction. So this is just a regular induction proof. Really the only difference is instead of starting at 1, we've started at 5. Everything else works the same way. Okay. Well, let's look at another generalization of induction. This is often called strong mathematical induction. And again, you can actually show that this is equivalent to regular induction, but this way of phrasing it just makes it more useful. So again, let's start at some number L. So instead of starting at 1, we're going to start, this is a more general case, that we're going to start with an integer L, and we want our result to hold for all n in S, namely all integers bigger than or equal to L. So again, we need to show that P of L is true. Okay? Our base case holds just like previously. But now our inductive step is going to change. We're going to assume that our hypothesis now for this inductive step is not just P of K implies P of K plus 1, but rather that all the previous statements imply the next statement. So P of L plus 1, P of L plus 2, and so forth, up to P of K. That all the previous things being true imply the next one is true. Okay? So this is the difference. We don't just assume that the last one was true, we assume that everything up to here is true, and based on that, we show the next one is true. And then if we can do both of those things, the result holds for all integers bigger than or equal to L. So let's do an example of this. So here's a result. Let theta be some real number, just some fixed real number. And I'm going to define a sequence of numbers, P0, P1, and so forth, recursively. So P0 is equal to 1, P1 is going to be cosine theta, and then I'm going to define all the future terms based on P1, Pn minus 1, and Pn minus 2. So based on Pn minus 1 and Pn minus 2 and P1, I get the next term. Okay? So this is just defining our sequence of numbers recursively. Well, if we do that, then Pn is equal to cosine n theta for all integers n bigger than or equal to 0. Okay, so I'm going to use strong mathematical induction based on, well, L is 1, because I'm going to be bigger than or equal to 0, and it's going to be strong mathematical induction because I need to assume that this thing here holds, and this recurrence, hold for all previous cases, and based on that, I'll show the next one. So let's look at a proof. Well, actually, before we get to a proof, we should remember a bit of trig quickly. So recall that cosine of the sum of two angles is given by this. Cosine of the difference is given by this. Okay? So just a quick reminder of a bit of trig there. All right, so let's prove this. So we prove the result by strong induction. So we're just alerting the reader to that we're using that slightly stronger statement of induction. Well, we're going to do the base case. So when n is 0, we have P0 is cosine 0 times theta, which is cosine 0, which is 1, as required. So the base case holds. Now, let's prove the next case. So we're going to assume that Pj is cosine j theta for all the previous cases. So we're going to assume that our result holds for 0, 1, 2, so forth, up to k. And now we need to build the next one. So let's consider the recurrence for the next term. The recurrence for the next term is P1, Pk minus Pk minus 1. So let's substitute in this. We've assumed that this is true for all the previous cases, and so we can just substitute those into this recurrence and make sure that it gives us the right thing. So Pk plus 1 is 2 P1 Pk minus Pk minus 1, and then it's just massaging some trigonometry around. So cosine of a difference is given by this. So cosine k theta, cosine theta, all of that mess just coming from here. Well, then we can see that this term cancels with some of that term, and we get this expression here, which is exactly the form that we need to make cosine k plus 1 theta. So we just have to massage things around a bit here, and based on our assumption that everything holds P0, P1, P2, all of those previous cases hold, and then we can show that the next term is given by what we want, so P of k plus 1 is true. So we can show P of k minus 1, all the way down to P of 0, implies P of k plus 1. So we've proved the inductive step. So the result holds for all integers n bigger than or equal to 0 by strong induction. Okay. Stop there.